So here we see that our juvenile axolotl is completely anesthetized, not moving at all while completely submerged in the MS-222, flipped on his back, meaning we know that he's asleep. And so we'll try to get some better images now of the regenerating limb and tail. So here's Mijo after 14 days of regeneration. You can still see the elbow right here. Yes, in order to anesthetize him, he was sort of, thrashing around, and he bumped his wound a few times, and so you see a little bit of blood cells at the end. But notice the clear red line, that's where he just bumped it. The white line, that's the regenerate. And then the dark line, that's where the stump is. So notice how large of a mound of cells there are now in the blastema regenerating from that whole region of white line. See if I can focus any better. Amputation plane right here. Everything you see from here on out is blastema. So this is a much bigger blastema. We only saw wound epithelium last time. Let's take a look at the tail. Same thing. See if I can change the lighting here a little bit. Clear tissue, all right here. Plane of amputation comes along like this. All of the tissue here, from this dark area out to the edge of the tissue, is the regenerate, the regenerating tail. So here's our tail with its fins, and all of this is new tissue from the last 14 days. The dark line coming up from the bottom left is the spinal cord. All the way to the area where there is no color left. That's the new cells forming a regenerate. So thank you, Mijo, for your wonderful regeneration. You've been growing beautifully. Next week we'll take those two blastemas and fix them in paraformaldehyde with the other limbs, the other tissue that we've taken, and we'll put it onto a microscope slide so we can look for proteins in the regenerate. And actually see what kinds of genes are used to make the process of growing a missing body part, fully regenerating it. What genes control that process?